Hello, this is Math 2231 coming to you from the College of DuPage for summer 2020, and this is a lecture entitled Review 4th of 4 and Properties of Limits. We're going to start with the limits. This, in fact, was the embedded quiz that you had, and these limits and the answer you should have turned in, a pretty easy 20 points, was that the limit as you tend to 0 from the right is 1, and the limit as you tend to 0 from the left is 0. Here is a problem I'd like for you to do. You know what to do. Let's see how you did. Well, you remember this oscillates from both sides, and therefore neither the right-handed nor the left-handed limit will exist. Here's another example for you to do. You want to compute the left and right, the left over here, and the right limit as x tends to 2 for this function. You know what to do. Let's see how you did. The limit in either case is 4. Here's a fact. Given a function f, if the right-hand limit and the left-hand limit are both equal to the same number, then the limit will exist, and the limit will be that common number. And likewise, if the limit as x tends to a of f of x is equal to L, then both the left and right-hand limits exist and also equal L. This fact can be turned around to also say that if two one-sided limits have different values, that is, the one from one direction does not equal the value from the other direction, then the limit does not exist. When I ask you to declare if a limit exists or not, and you say it does not exist, I ask you to justify it. This is one of your justifications that will be accepted. I probably would expect you to say what these different limits were as well, to underscore the point. Okay, here is a problem. You're supposed to compute each of the following, and here's the graph of f of x. You know what to do and when to do it. There are L parts to this problem. Let's see how you did. I would suggest maybe pausing here to check your answers and make sure you understand anything that you miss. Here's the graph that you used, and here are the answers. Make sure you follow up with John or Jesse should you miss some of these, or me should you miss some of these. Here are the rest of them. Again, it's worth spending some time on this chart to make sure you understand this. This is fundamental. Here are some properties of limits that we'll use in computations. If we take the limit of a constant times a function, that is equal to the constant times the limit of the function. What that means operationally is you can jerk the constant through the limit sign. Here, the limit of the sum as x tends to a of the sum or difference is equal to the sum or difference of the limits. What this means is you can do limits term by term. Terms are separated by plus or minus signs, so you can do limits term by term. The limit of the product is the product of the limits if all of these limits exist. The limit of the quotient is the quotient of the limits, provided the limits both all exist and the limit as x tends to a of g of x does not equal to 0. Here, what you're really saying is you can just plug it in. Here again, you can just plug it in. The limit as x tends to a of a constant doesn't depend on x, is just the constant. The limit as x tends to a of x is just a, and here you can just plug it in. You heard a lot of just plug it in. There's a reason for that. Here's a problem for you to do. So you compute the value of this, you know what to do. Let's see how you did. You should have gotten -7. You do it term by term and you pull the constants through. And in fact, you can generalize that exercise to say, oh, if p of x is a polynomial, then you can't just plug it in. This is the takeaway. Although it does not always work, and especially in this class, the first thing to consider, if only for a nanosecond, when you're computing a limit is just plug it in. Evaluate this limit. You know what to do and when to do it. Let's see how you do. Your answer should have been 13 over 6. Here's another fact. Provided that f is nice enough, we have that you can just plug it in from the left and from the right and for the function itself. Now very soon we will deal more rigorously with what it takes to be nice enough, but for now just realize the first thing you try when computing a limit, if only for a nanosecond, is just plug it in. And here's a list of many common functions that are nice enough. This is a lot of functions. In particular, if we have any sum, difference, or product of the above functions, will be nice enough as well. We really can compute many limits using our tools. Here's a problem. You're to evaluate this limit. You know what to do. Let's see how you did. Now I hope you did not use a calculator, because you're not going to have a calculator to use on tests or serious quizzes. But this is a just plug it in. So now each of these things, many of these things, the sine of 3 and the cosine of 3, those are sine and cosine of 3 radians. Those are irrational numbers. You don't know what they are. E cubed is an irrational number. You don't know what that is. Ln of 3 is an irrational number. You don't know what that is. Negative the fifth root of 3 is an irrational number. You don't know what it is. This is the answer. Now some of my students would say, Jim, that's the ugliest damn answer I've ever seen in my life, the ugliest number I've ever seen in my life. But I would tell them there are no ugly numbers, just like there are no ugly babies. See you in 7.